Okay, let's try another LaGrange multiplier method problem. And this is also written up in your notes. And we've got a cargo container, a rectangular solid, where you're required to have a volume of 480 cubic feet. Now, the material cost for the bottom of the container is $5 per square foot, and the material cost for the top and the sides is $3 per square foot. Now what we're asked to do is minimize the cost and find the dimensions that will actually do that. So just like we're doing a Calculus 1 problem, we set this up with positive variables here. We could let x be the length, y be the width, and z be the height in any order you like. Now again, this volume here is a constraint, and we are solving this with the LaGrange multiplier method, so we always have to have a constraint, and you can even have more than one constraint. You just end up with more complex equations. So now what we want to do, if we're going to minimize the cost, we need the cost of building the container. And so we're going to have the material for the bottom, which will have an area of xy. The cost will be 5xy. And then all of the other parts of the box, the sides and the top, all cost $3 per square foot. And so when we think of the two of the sides, that is, two sides will have area xz and two sides will have area yz. We multiply both of those by 2. And then, of course, the top just has the area xy, only one of those terms. And then, of course, when you collect terms, you get 8 copies of xy, 6 of xz, and 6 of yz. Now, we can actually write the problem based upon this. That is, minimize f subject to the constraint here, that is x times y times z, which is the volume of the container, must be 480. So now we have our constraint. We can take our gradients. Again, in the LaGrange method, we'll see that the gradients will actually be parallel. So these gradients are easy to compute. Remember the x partial, y partial, z partial for f, and then for g, the x partial, y partial, z partial. Very simple to compute. Now again, we know that these are parallel, so we'll have 8y plus 6z is equal to lambda times yz. That's our first equation. And then we'll have 8x plus 6z is equal to lambda times xz. That's the second equation. And then we'll have 6x plus 6y equal to lambda times xy. That's the third equation. Now when we look at these three equations, they look a little more complex than the last problem, but with some easy algebraic maneuvering, we can make this problem very doable. So what we can do, and remember, our techniques are not unique. This LaGrange method is kind of like magical because they're necessary conditions. We don't look at this the same way as we do the second derivative test. But notice if we multiply the first equation by x, the second equation by y, and the third equation by z, we'll get the same term right-hand side here for all three equations. And so that makes it very simple to analyze. So if I look at the first two, what you notice here is that the 8xy terms will absorb, and we're left with these two terms. That is 6xz equals 6yz. Again, z is positive, so it absorbs, and we get x equal y. Now, of course, you can go ahead and substitute into one of these equations and move it forward that way, but I thought I'll just go ahead and repeat myself like I did for the first two. Notice again that when we actually set these two equations equal, these two will absorb, they're equal, but then that gives us 8xy equal to 6xz. Again, the x is positive, so it will absorb, and we get 8y is equal to 6z. If we solve for z, we just get 4/3 y. Now, what makes this really simple now is that we can move forward with this. For instance, notice that z is equal to 4/3 y, so we can just put that in from the constraint equation. And then we know that x is equal to y, so we can just put in y for y and y for x. So now we just have an equation in terms of y. So when you multiply this, that is, you can divide by 4/3, and that'll basically just give you 3 times 120, or 360. So y cubed is equal to 360. Take cube roots, we get y is equal to the cube root of 360. And 360 doesn't have any perfect cubes in it, so that's about the best we can do with it. And so now, there you have it. We have our critical point. That is, x is equal to 360 cube root, y 360 cube root, and then z 4/3 times the cube root of 360. Again, this is something that just falls into your lap, and what you see here is that it would be very easy to make this value larger, but through the LaGrange method, we actually do find the dimensions that will actually minimize the cost, and we have indeed minimized the cost. And we are done.